Welcome to AI's Big Day Machine Learning Breakthroughs. Today, we spotlight 68 newly released papers, each a fresh spark of innovation in machine learning research as of August 25, 2025. This episode explores how artificial intelligence is reshaping science and technology, guiding you through recent breakthroughs, emerging methods, and forward-looking paths in modern AI. This presentation will provide a comprehensive overview of the latest trends in machine learning research. Listeners can expect to learn about major themes shaping the field, examine standout papers and their real-world impacts, and gain accessible explanations of complex technical concepts. Insights into where artificial intelligence is heading next will be offered, equipping both newcomers and experts with a clear guide to the current state and future directions of AI. Machine learning is an area of computer science where algorithms learn from data to make predictions or decisions. Its applications span natural language processing, computer vision, robotics, and scientific discovery. The field encompasses supervised learning, unsupervised learning, and reinforcement learning. Machine learning underpins advances in domains such as medicine, finance, and planetary exploration, driving both foundational theory and practical solutions that address real-world challenges. A prominent research theme is efficient and robust learning, crucial for deploying AI in environments with limited resources. Techniques such as adaptive batching for distributed model training, highlighted by Smith and colleagues, and optimizers, resilient to noisy, non-stationary data as proposed by Lee and collaborators, exemplify this effort. The central goal is to maximize learning efficacy while minimizing resource expenditure, akin to a chef crafting gourmet dishes with only a handful of ingredients. Robust optimization remains a key concept, ensuring AI systems deliver reliable performance under real-world operating conditions. Interpretability and trust in AI represent another critical research direction. New frameworks, such as those introduced by Geneseo and colleagues, provide explanations for molecular property predictions. Techniques for detecting label errors and quantifying uncertainty, as developed by Chen et al., enhance reliability. An illustrative example is counterfactual masking, where explanations are grounded in chemically realistic modifications. In practice, experts require actionable and trustworthy AI insights. Counterfactual explanations, showing what-if scenarios using plausible changes, are central to making machine learning outputs transparent and actionable for domain specialists. Advances in deep learning and representation learning continue to drive the field forward. Recent work includes transformers adapted for scientific datasets, as seen with Kumar et al., and mixture of experts models developed by Wang et al. Notably, Kratsios and collaborators have demonstrated that neural networks can systematically emulate any algorithm. Quantum classical hybrid models are also being explored to tackle complex problems. The technical concept of universal function approximation is underscored here, establishing that neural networks can, in principle, model any computational process. Learning on complex data structures and enabling scientific discovery is a key theme in recent research. New graph neural network architectures, such as those developed by Park et al., are designed for intricate data relationships. Spectral and manifold learning methods, discussed by Liu et al., address time series and high-dimensional data. Domain-specific breakthroughs have been reported in biology and chemistry, including AI-assisted protein design with limited data. As exemplified by the work of Sui et al., machine learning is increasingly viewed as a collaborative partner in scientific discovery, capable of advancing research across diverse disciplines. Reinforcement learning and intrinsic motivation are central to equipping AI agents to seek and adapt within complex environments. Techniques such as dynamic reward scaling, proposed by Garcia et al., and intrinsic motivation driven by large language models, as demonstrated by Patel et al., have expanded RL capabilities. Decentralized teams of learning agents are being studied to tackle problems with scarce and delayed feedback. These advances enable artificial intelligence to learn effectively, even when explicit rewards are faint or sporadic, further broadening the application space for reinforcement learning. Key findings from the 68 reviewed papers highlight significant breakthroughs across machine learning. Kratsios et al. Have shown that neural networks can exactly emulate any algorithm or circuit. Mayer et al. Improved quantum circuit training through reinforcement learning, addressing issues such as vanishing gradients. Zhou and collaborators developed normalizing flow models capable of generating novel molecular conformations. Janisau et al. Advanced actionable and realistic chemical explanations through counterfactual masking, while Sato et al. Introduced adaptive neural network systems for real-time crater detection in planetary exploration. Collectively, these achievements exemplify the field's rapid progress. A variety of technical methodologies have powered recent advances in machine learning research. Reinforcement learning with dynamic rewards and hierarchical structures has improved agent learning in complex environments. Flow-based generative models have enabled efficient sampling from intricate data distributions. Sparse autoencoders facilitate interpretable and compact representations, leading to greater model transparency. Robust optimization techniques are employed to ensure reliability in safety-critical applications. Innovative neural architectures for graphs and manifolds further expand the modeling capabilities of artificial intelligence systems. The foundational paper by Kratsios et al., titled Quantifying the Limits of AI Reasoning, Systematic Neural Network Representations of Algorithms, demonstrates that neural networks can emulate any algorithm or logic circuit exactly. The method utilizes a systematic translation from logic gates to neural modules, moving beyond the universal approximation property to encompass exact reasoning capabilities. This work establishes a new theoretical baseline for what neural networks can achieve, and is recognized for its profound implications and foundational impact on the field of artificial intelligence. The work of Sui et al., Sparse Autoencoders for Low-End Protein Function Prediction and Design, introduces an interpretable approach to protein engineering using protein language models, coupled with sparse autoencoders. This methodology excels at predicting protein function with limited experimental data, leveraging latent variables that align with meaningful biological features. The resulting models enable actionable protein design in data-scarce settings. This paper was selected for its innovative contribution to interpretable, low-data artificial intelligence within the domain of computational biology. Janisau et al.'s paper, Enhancing Chemical Explainability Through Counterfactual Masking, represents a significant advance in molecular property prediction. The method replaces masked molecular substructures with chemically valid fragments, ensuring that explanations are both realistic and actionable. Comparative studies demonstrate improved robustness and utility over standard masking techniques. By bridging artificial intelligence predictions with practical chemical design, this approach sets a new standard for explainable machine learning in chemistry and related domains. Future directions in machine learning research are defined by several emerging priorities. Models that are transferable and adaptable across new domains, as described by Zhou et al., are gaining prominence. Ongoing improvements in explainability and uncertainty quantification are essential for broader adoption. Research into efficient learning for edge devices and resource-constrained environments continues to expand. The integration of AI with scientific and engineering workflows is deepening, and theoretical advances are clarifying the fundamental capabilities and limits of artificial intelligence. This presentation was synthesized using GPT 4.1 by OpenAI for summarization and narrative construction. Speech was generated with DeepGram TTS, and visuals were created using Google Image Tools. All content was reviewed by human experts for clarity and accuracy, although some oversights may persist. References are provided for verification, and all cited sources follow the first author et al. Format throughout. Thank you for joining us at AI Frontiers. Subscribe to our YouTube channel for more insights into artificial intelligence research and join a community passionate about the future of machine learning. Stay updated on the latest breakthroughs and expert analysis. Your journey at the frontier of AI starts here. In this podcast, we bring you the latest breakthroughs in computer science and AI straight from the arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.